Hello everybody, my name is Mr. Tippett, if you haven't seen me in a while. Today we're going to talk about gas laws, in particular Boyle's Law. Boyle's Law deals with pressure and volume. Now, there's four gas law variables: pressure, volume, temperature, and the number of particles. Boyle's Law only deals with two of those variables, pressure and volume. What we're holding constant is temperature and number of particles. Now, what that means is the temperature is constant, it's not changing. Number of particles isn't going to change. I got here so you can see it, a nice little Nerf rocket. This is a pretty good example of, back up so you can see it here a little better, Boyle's Law. So when we expand the tube out like this and pull the tube wider, what we've done is increase the volume. Now, if I quickly discharge this and make the volume rapidly, watch this, whoo! Can't see it, but the rocket just went that way. See? More rocket. Volume rapidly decreases, the pressure inside builds up, therefore the pressure, when it's larger than a frictional layer, launches a rocket. Number of particles might change slightly, but in that quick time where you're decreasing, the number of particles are being held constant. Temperature in the room, constant as well. So, when you have one variable going up like pressure, one variable rapidly decreasing like volume, what kind of relationship is that? So when we have one variable increasing, one variable decreasing, we're going to refer to that as an indirect relationship. Now, it could be the other way as well. We could have one go down and the other goes up, but the variables are going to work in opposite directions. Mathematically, how do we solve that? How do we work with that? So I'm going to run through an example on how we set our formula. So let's say you have an initial pressure of 1 atmosphere. Atmosphere is the unit we work with pressure on. An initial volume, let's say you have 10 milliliters. So in an indirect relationship, we're going to take P times V as our base formula. It's going to give us a constant, which is K. So that constant in this situation is going to be 10. Pressure of 1, 10 milliliters. We're going to get a constant K of 10. Now, let's say we have a second volume, P2, and a second pressure, V2. So volume 2, let's say we cut it in half, like the rocket we just launched. Let's say we cut the volume from 10 to 5. So if it's 5 milliliters, what happens to pressure? Well, if you take the same particles, decrease the volume, there's going to be a lot more collisions. Therefore, our pressure is going to go up. How much? Well, if you take the volume, cut it in half, pressure is probably going to double, right? So it's going to be 2 atmospheres. Well, 2 times 5 still gives us our constant of 10. Well, if our initial pressure, our initial volume equals 10, and our secondary pressure, our secondary volume equals 10, well, if P1 times V1 equals 10, P2 times V2 equals 10, can't we just take P1 times V1 equals P2 times V2? Well, having that, this is our formula for Boyle's Law. Okay? So knowing that formula, we can use that to solve a sample problem. Now, this problem is one like you could get worked up several times. If you look at the problem, it says, a sample of nitrogen collected in the lab occupies a volume of 735 milliliters at a pressure of 0.95 atmospheres. The first thing we're going to do anytime we get a word problem like this, a gas law, we're going to make a list. So the first thing, make a list. Let's identify what we have. So a sample of nitrogen occupies a volume of 735 milliliters. So V1 immediately, 735 milliliters. At a pressure of 0.9 atmosphere, that's our initial pressure, P1, 0.95 atmospheres. What volume in liters? Okay, so that's our V2. X liters. Well, the gas occupied a pressure of 150 kPa. So our P2 is 150 kilopascals. Well, that's a different unit. Assuming temperature is constant. So the gas is trapped, particles the same, temperature is constant. So we have temperature, particles the same, two variables changing. We can identify that, use Boyle's law. Before I can plug it in, now it basically turns into an algebra problem. Because we know we're going to use P1 times V1 equals P2 times V2. Before we can plug those in, though, we got to make sure our units are all the same. So if I look at milliliters, here I want liters. Before I plug it in, I got to have the same unit. So I'm going to convert my milliliters to liters to start. 1 liter. So that's going to be 0.735 liters. I'm looking at atmospheres. kPa, two different units. Okay, we'll talk about this a little bit in class, how to convert pressure, but the units we're going to use, cancel out kPa, get it to atmospheres. 1 atmosphere equals 101.3 kPa. We'll cover that in class, get joules equalities. And when you plug that in, 150 to 101.3, did the work a few minutes ago, that comes out to 1.48 atmospheres. So, liters and liters, atmospheres and atmospheres. Now it basically turns into Boyle's law. If I plug it in and use algebra. So I can help you there, make this a little larger for you, easier to see. P1, V1, P2, V2. My initial pressure, 0.95 atmosphere off my list. Initial volume, 0.735 liters. P2, 1.48 atmospheres. V2, what I'm solving for, X. All right, now it turns into an algebra problem. Gotta get everything on the same side. Divide by 1.48 atmospheres. Cancel my units, cancels out. Whatever I do to one side, have to do the other. 1.48 atmospheres. Those cancel out. Good self-check. Whatever I have, that's the label I want. Bring it down, liters. X, 0.95 divided by, or times 0.735 divided by 1.48 should come up with 0.47 liters. Last thing when I ask myself, does my answer make sense? Well, my pressure went from 0.95 to 1.48, so my pressure went up. I know this is an indirect relationship, so if one goes up, the other must go down. Well, my volume went from 0.735 liters to 0.47, a decrease, so it makes sense. Thanks for listening to the Tippett Network.